Hello, everyone. Welcome to this Datadog episode. This time we are going to be talking about Kubernetes node management. Datadog is a series of events where we invite engineers working every day on Datadog, on building Datadog, to talk about what they do on a daily basis. So some technology, some process they follow, etc. So some housekeeping items. So the goal of this series as well is to get a lot of questions from the audience. So please prepare your questions throughout the event. You don't have to wait until the very end to ask your questions. You will see, if you're in Zoom, you will see a Q&A button in your Zoom client. Use the chat window to chat among your peers, but use the Q&A button to ask the questions. And at the very end of the presentation, we will go through the list. If you happen to be live on LinkedIn, to ask a question, just leave a comment on LinkedIn and we will get to those as well. Good. This episode, as every other episode, is going to be recorded. So if you want to watch it afterwards or you want to share with a colleague, in a couple of days will be available in YouTube and datadogon.datadoghq.com, as well with any other past episode in case you're interested. Okay, so before we get started, this episode and these events are not about Datadog itself as a product, but how we build Datadog internally. But just so you know, Datadog is a platform that helps companies improve observability and security of their infra and applications. And my name is Sara Pulido. I'm a Star Developer Advocate here at Datadog. I'm one of the co-organizers of Datadog. So if you have any feedback or if you want to suggest a topic that you want us to cover, please reach out. But the important people today are Adrien and David. Adrien, do you want to introduce yourself?
Yeah, my name is Adrien Trouillaud. I'm the engineering manager for the compute node lifecycle team here at Datadog. I live in the United States near Seattle.
Good. And David?
Hello, my name is David Benque. I'm working from the south of France. I'm a staff engineer attached to the compute team. The compute team is responsible for running the Kubernetes clusters for the rest of the company. I'm focusing a lot on auto-scaling, pods, nodes, runtime cost, and of course, node management.
Thanks both for joining us today. Usually on these episodes, we touch briefly on Datadog scale because some of the decisions that we make are related to that scale that we run on. So Datadog is an observability platform that has more than 25,000 customers, and we collect telemetry from those customers. That adds up to millions of hosts that we collect telemetry from and translate to tens of trillions of data points per day that we need to ingest and process. And Datadog itself is run on Kubernetes. So we use Kubernetes as our infrastructure platform, and we run very large Kubernetes platforms, dozens of clusters, some of them with thousands of nodes that translates in hundreds of thousands of pods. And we run those clusters on different clouds. Another thing that we do is that we manage our own control plane. That basically means that we are not running one of the managed Kubernetes platform that the public clouds offer. And the reasons is because we need, because of the scale that we have, we need to tweak a lot of things on the control plane itself. We are going to not talk about the part of the control plane that controls the core of Kubernetes components, but the nodes. And we thought that it would be interesting to think about nodes in a Kubernetes cluster by trying to see a high-level overview of the life of a node. So, David, do you want to tell us what happens in the life of a node at Datadog?
Sure, can do that. So let's start with this node being at the center of the picture here. So the node in Kubernetes is the place where we are running our applications. Applications being pods in Kubernetes, pods themselves being set of containers that are going to run on this machine. During the life of this machine, some application may require some disk space, and we may have to attach and detach volume from this machine. Also, for this machine to communicate with the rest of the infrastructure, we would have allocated an IP to this machine. And before running anything, in fact, on this machine, we need to go through what I would call the provisioning phase. We are going to detail this phase later on in this episode, but I would say that at the end of this provisioning phase, we end up with a node resource inside Kubernetes. And at this time, controllers in Kubernetes can start watching this resource. And for example, the kube scheduler will be able to bind your pods onto nodes. So somehow the kube scheduler is the one turning your pending pods into running pods. But let's come back to the node itself. At some point, this pod on the node are going to terminate. And this will leave us with an empty node. And of course, we don't want to keep an empty node because it's going to cost us money for nothing. So we will go to the retirement of this node. And this is done in Kubernetes by the cluster autoscaler. Each time the cluster autoscaler sees an empty machine, it tries to remove it from the cluster and give it back to the cloud provider. So unused node is one of the reasons of going to the retirement phase. But there are many other reasons beside unused node that would lead you as a platform operator to force this retirement phase, if I can say, or you want to provoke it. So let me give some example. We can have like broken node, for example. What do I mean by broken node? If you're running Datadog and you have an observability, this observability can tell you like, oh, you know what? I see logs coming from the kernel saying that we have this corruption. And of course, you don't want to run your application on such a node, so better leaving this node. So you would quit this, you would do the things that you need to terminate the pod and to go somewhere else. One other reason may be that you need to update that node. What do I mean by updating the node? To run, a node needs an application, an operating system. To run containers, it needs like a container runtime. To be able to register to Kubernetes, it needs to run a kubelet. And all these things are version software that run on the machine. And as any software that is versioned, at some point you need to bump the version because there are some vulnerability or you need a new feature. So this is what I mean by an update of the node. It could be also that the cloud provider is telling you that the rack is going to go under maintenance in 1 week from now, and it would be better if you can stop the machine and stop gracefully your application. Or the cloud provider can also reclaim the machine because you're running some, for example, spot instances and they are being reclaimed like periodically. Finally, another reason could be optimization that you as an operator of the platform decide. It could be like, you need more bandwidth, you need more CPU, and you need to change the instance type. Or it could be because you need to change the architecture, or you need to reduce the cost by using a different instance type. So to enter this retirement phase, we need to empty this node for all these reasons, and we do what we call voluntary disruption, meaning that we're gonna stop the application that is running on this machine. So voluntary disruption is just one kind of disruption, and it's the one allowing us to do graceful stop of the app. But there are other kind of disruption that we call involuntary disruption. Power cut. Obviously, the machine is not going to run anymore. Hardware failure, network partition. You have a list here. It's clearly not exhaustive, but this one is a brutal stop of the machine. No graceful termination of your application, if I can say. So yeah, this leads us to the end of the life of the node. And I will conclude this overview with this, I think.
Good. Thanks, David. So let's go by each of those phases step by step, because obviously a lot more goes into the details. And obviously we start with provisioning those nodes and autoscaling them, because provisioning an instance in the public cloud might be easy. They have very rich APIs that you can call in different ways. But when there is thousands of VMs that needs to be provisioned, things might get a little bit more complicated. Adrien, how are we solving this at Datadog?
Yeah, that's right. So we need to provision a lot of virtual machines that become Kubernetes nodes. And so the cloud providers offer APIs that allow you to manage VMs as groups. So in AWS, it's an autoscaling group. In GCP, it's a managed instance group. In Azure, it's a virtual machine scale set. I'll just call them ASGs. And so at Datadog, we have an abstraction to create and update the ASGs that we call the node group. It's a Kubernetes custom resource. And we have a controller called the node group controller that we wrote in Go using the controller runtime library. And that's the one in charge of reconciling the node group custom resource objects in the clusters with the cloud resources. And then once the groups are in place, the cluster autoscaler, which is an open source tool maintained by the special interest group Autoscaling, that tool is responsible for the scale ups and the scale down. So what is a node group? Let's have a look at what a node group looks like. So like any Kubernetes resource, it has a YAML representation that you can work with in your charts. Some of the node groups are managed by the compute team in a centralized fashion to answer most use cases. And some node groups are managed by application teams if they need special nodes. The only required field is actually the instance type. That the node group I show here on the slide, that's enough to provision the ASG. But it's customizable. Like if you want more ephemeral storage or to tweak the network settings, there are a bunch of other fields to do that. But the node group controller ensures will configure the ASGs with the right defaults, tags to be discovered by cluster autoscaler, to be in the right subnet for networking to work to function in the cluster, have the right machine image that includes the kubelet, etc. For the VM to be a Kubernetes node that will join a cluster. So how do these nodes show up? So we run an elastic infrastructure. So we don't necessarily, it's not static, right? It answers to pending pods. So when a pod is created by workload, deployment, stateful set, etc., the pod at first is pending. It doesn't have a node yet. So if there is an existing node in the cluster that could fit the pod, the Kubernetes scheduler is able to place the pod. But if there's no existing node that could fit the pod, then cluster autoscaler jumps in and it tries to match the pending pod with one of the ASGs. So part of the tags on the ASGs is like what the labels would be, what the allocatable resources would be on the node that would come from that ASG. And so the cluster autoscaler is able to create that representation of the would-be nodes, do the matching, and scale up the ASGs. So ASG is scaled up, an instance is created, it registers with the Kubernetes API server to become a node. And finally, the scheduler sees the node and can bind the pod with the node. That's called scheduling. And yeah, the pod can start. So containers are started on the machine, and it's the life cycle of the pod, which is not the topic of today's conversation.
Good. Thanks, Adrien. It's also good to see that some of the abstractions that you came up with are actually abstractions of things that are open source, like the cluster autoscaler that we are just reusing through those. So obviously scaling out is very important to support growth, but equally important, I think, is to be able to manage the cluster, and also for cloud cost concerns is to be able to scale down. So David, how do we scale down a Kubernetes cluster?
Yeah, it's very important to scale down, not to run empty machines and pay for nothing to our cloud provider. So as we can see on the slide, and as said by Adrien earlier, the empty node is collected by the cluster autoscaler. And I would say that we're going to try to stick to this path to do the scale down. Like we want to reach the state where we have an empty node to do the scale down. And what I'm going to discuss in the next slides is how we get there. How do we get an empty node? But by terminating pod, it's a good way of having an empty node. And the natural way of doing that when you run applications is to play with the deployment itself. By terminating the deployment, obviously, you remove all the pods, but also during a rollout phase, because you're going to replace pod and new pods may go to a different machine. So the pod running on a node is going to terminate. With automation in Kubernetes, you have controllers that deals with horizontal scaling of pods. Here I'm mentioning HPA and WPA that are horizontal pod autoscaler and watermark pod autoscalers. These play with the number of replica in a deployment. And so by reducing this number of replica, you terminate pods. So that's one way, but there are other ways. Let's see one that is happening when we have a node that is failing. Let's say that the common pattern here is the node is not sending any more heartbeats to the Kubernetes API server. So the kubelet is not communicating anymore with the cluster. So the controller manager in Kubernetes will notice this, and it will taint the node with two taints. The first one being no schedule to ensure that the scheduler is not going to put any more nodes. And a second taint that is called no execute. This no execute taint is going to trigger something called the taint-based eviction. The taint-based eviction terminates pod on the node, leading us again to an empty node that can be collected by the cluster autoscaler. So this is the second way. The third way would be consuming the pod eviction API. So what is this API? If you're operating in Kubernetes, you may have used a command called kubectl drain. And behind the scene, it's consuming this pod eviction API. kubectl drain is cordoning the node so it prevents any more schedule on that node. And then the drain is sequentially calling the eviction API for every single pod running on the node till the node is completely empty. So these are the common way of doing this. There is yet another case that is called eviction that I would like to mention here. It's eviction done by the kubelet itself. But this does not lead to an empty node. It's just in case of pressure on the machine, disk pressure, memory pressure, the kubelet can stop some containers. I want to mention this because it's called eviction, but it's not going through the eviction API. Okay. So if we go back to the reasons that I have exposed earlier, obviously the node being unused and terminated is what we have explained from the beginning, cluster autoscaler taking the node down. If a node is broken, we have seen that in some cases, the controller manager can do something. If the node is half broken, like disk corruption that Datadog can notify you, but the controller manager doesn't know about, this case is not fulfilled. I mean, we are not going to be able to do anything with what is on the screen. And for all the other cases, it's the same. We don't have any automation here in place to help with these cases. And this is why at Datadog, we have started to introduce a new set of controllers that we call node lifecycle controllers that are going to consume the eviction API to build automation that will allow us to cover all these cases. And during this presentation, we're going to explain all of these controllers. And now on, we're going to reuse these slides. And there is a kind of color code. Everything that you see in purple is something that we run at Datadog. And everything that you see in blue is coming from Kubernetes itself.
Good. Thanks, David. Yeah, so we are going to start filling up this graph with all the different pieces that form this node lifecycle automation. But let's before that, let's discuss a little bit more the Eviction API, because it's super fundamental to everything that your team is doing. So Adrien, do you want to go a little bit deeper on what is the Eviction API and why it's so important for the work that you're doing in your team?
Sure. And before we discuss the Eviction API, actually, I want to introduce two concepts, the readiness probe and the pod disruption budget. So a readiness probe is something that you specify on a workload's pod template for each container. It can be an HTTP call, a TCP call, a command, a gRPC call, I think. And if it's successful, the primary use of the readiness probe is to say that, so if the call is successful, for all containers, the pod is considered ready to accept traffic. So its IP is registered as an endpoint for service. Now, the readiness probes are reused for the pod disruption budgets. And a pod disruption budget is something that tells Kubernetes when it's okay to evict pods. So just like a service, it has a label selector to say which pods it covers. And then it says, it has a pretty simple language to specify when it's okay. So for example, only one pod is allowed to be unavailable. Max unavailable equals 1. You can also specify in terms of minimum, in terms of relative or absolute numbers. But max unavailable equals 1 is sort of the safest bet. Like only allow one pod to be evicted in the pods that are covered by this PDD, which is typically the workload. So to illustrate that, I drew some pictograms on the right. So let's look at the one on top in the upper right corner. And so in blue are the pods that are ready, in gray the pods that are not ready. So first case, all pods are ready. When all pods are ready, all 3 replicas of the stateful set, any pod can be evicted. Not all of them at once, of course, but because that would change how we are compared to the budget. But any pod can be evicted. Now, if one of the pods is not ready, you cannot evict the ready pods, because that would mean that there would only be one left that's ready. So, but the pods that is not ready can be evicted. And that is because if it's evicted, like, it doesn't change the number of ready pods. There's still 2, and we're still within budget. And it becomes tricky or like a little different when there are more pods that are unhealthy. You'll notice that I use the words ready, available, healthy kind of interchangeably, and like in the context of Kubernetes eviction, they're sort of synonyms. Yeah, so it's pretty much the same. And so yeah, we're not within budget anymore in number 3 and number 4 there, where we have 2 pods that are not ready. And so what's allowed to be evicted here depends on a policy, the unhealthy pod eviction policy. For the pod that's ready, in any case, don't evict it, because that would for sure make things worse. You would have no pod ready after that. So the first one, don't evict it. But the pods that are unhealthy, if you use the default policy, which is if healthy budget, like you cannot evict them, because you've already consumed your budget. So don't evict any pod. But if you use the new policy that appeared in Kubernetes 126 as alpha, 127 as beta, you can actually tell Kubernetes to say that it's okay to evict unhealthy pods. And so the 2 last ones, if you use that policy, can be evicted. So be careful there, however, because you can tell yourself, well, it's already unhealthy. Like, what harm could it do to evict it? It's already not working. But if you have a stateful application, maybe you have data that is stored and hasn't been persisted, the application lost quorum. So like a pod that's unhealthy doesn't mean that it's a pod that's already gone. And so evicting it could actually make things worse. You could lose data. So be careful if you decide to use the always allow policy. Now we can talk about the Eviction API, because the Eviction API checks pod disruption budgets. So eviction is a pod sub-resource. By that I mean that it's an endpoint on the Kubernetes API server under pods. So the clients create eviction sub-resources on pods. And so if the pod disruption allow eviction, the pod is terminated and status return is okay. If the pod disruption budget doesn't allow the eviction, the return code is 429, retry later. The nice thing, there are 2 nice things actually about Eviction API being a pod sub-resource. First of all, like with any resource in Kubernetes, you can plug in admission webhooks. So you can validate the requests, also mutate them. But in this case, we don't use that. We care about validating, especially because we'll see that pod disruption budgets don't cover all use cases or edge cases. So it's convenient to have this point that where you can attach more checks, synchronous checks in this case, to validate the eviction. The other nice thing about it being a sub resource is that it can be run as a dry run. So as a dry run, like with any resource in Kubernetes, the request goes through admission. So you perform all the checks. Then it also checks the pod disruption budget, and it returns 200 or 429, but it doesn't terminate the pod. So you can run dry runs on all the pods of a node, for example. We call that a simulation, and only stop draining if you can actually evict all the pods. Because if you don't want to end up with a pod that is half empty. That's not optimal. That could delay things. Yeah, so that's very convenient. So pod disruption budgets are really a really useful tool to protect your workloads. So at scale, we have hundreds of thousands of pods to make sure that all the pods that we care about are covered by PDBs. We need to enforce that the PDBs cover them. And so, like with any operational enforcement issue, you could either detect the problems, bug the user about it, say, hey, add PDBs, add PDBs. That would have been option one. We could have checked, in CI, at admission, in different stages of the software development lifecycle, if you want. But we always prefer to make things automatic. And so option two, which we selected, is to create default PDBs. So by default, any workload, so deployment, stateful set, etc., has a default pod disruption budget that we have an internal tool at Datadog that does that. That's not in Kubernetes core, but we do that. So when we choose a conservative sane default, max and available equals 1, which is the safest bet. And if users say that they would actually want to cover more workloads with a single PDB or allow 10% pods to be unavailable, they can always create custom PDBs, and we'll delete the default ones. Yeah, so that's so it's easy to say, right? Just create the default PDBs, but actually you have to. It's not that easy. One thing with PDBs that you have to be careful with is that they should not overlap. What I mean by overlap is if one pod is covered by two different PDBs, if the label selector of two PDBs matches the same pod, then Kubernetes doesn't know which PDB to check and prefers to say, I don't know, fix your configuration. So it returns a 500. And so for our default PDBs, to make sure that we don't have overlaps, we instead of trying to select carefully the pods that already exist on the labels that already exist on the pods, we added a label on each pod that is the workload, so the deployment stateful set UID, and the default PDB selects that label. So in a way, we're selecting workloads, and so there are other we're not using the label selector is too flexible for us, and you could have thought. We think that it'd be convenient if Kubernetes offered a way to just select workloads. There are other resources in Kubernetes ecosystem that select workloads rather than use label selectors, like the horizontal pod autoscaler, for example, or vertical pod autoscaler. Yeah, that would make some things simpler. That's all.
Thanks. So you've mentioned at the beginning on talking on readiness probes and PDBs that readiness probes are used for two things in this case. Why is that a problem in some cases?
Right. Yeah. So the primary use of a readiness probe is to say pod is ready to accept traffic. The readiness probe is reused to say when it's okay to evict. So in most cases, that works. You can, with the same probe, you can find a success set of conditions for that return a success for the readiness probe. That's that is a good combination of receiving traffic and being okay to be evicted. But the problem is when you must receive traffic, but maybe it's not the right time to evict. And in Kubernetes, there's no way to independently control disruptability and service readiness. And that's why we had to extend the pod disruption budget. And so let me give you a few examples about what I mean by you must receive traffic, but not okay to be evicted. So for example, your application is receiving traffic, but is under pressure. So of course you must continue to receive traffic, but if you remove one pod, you can be even more under pressure. So like eviction is not the right thing to do at the moment. Or it's under maintenance. There's an update, for example, of an image or more complex maintenance operations happening. And so if you evict some pods in the middle of that could disrupt the operations or delay things. So it might not be the right time either. And finally, if there's an incident, it might be related to the application, maybe not, maybe you don't know yet. And so having evictions happen in the middle of that, of the investigation, could delay the investigation. It could make the incident worse. So we have ways to stop or block evictions during incidents. To do that, we created a tool called the Disruption Budget Manager, and it can dynamically reduce the budget of pod disruption budgets. And talk about the first example, when the application is under pressure, we can detect that in Datadog with metrics, and monitors are triggered in that case. And so the Disruption Budget Manager watches the monitors, and when they're triggered, it reduces it changes the spec of the PDBs to set max unavailable equals 0, for example. And we do the same actually for the maintenance use case. So when our deployment platform rolls out an update of a service, it can take a lock in a distributed lock system that we have internally at Datadog. And when the lock is taken, the budget is reduced also using the same dynamic spec update. Now for incidents, you may want to change the many pod disruption budgets. You want to block evictions across many workloads, for example, in an entire zone, entire data center. I don't know. So we're not going to mass update the PDB specs in that case. So in that case, what we do, we intercept all eviction requests, and at admission, we can say when there's an incident, don't evict, and we block the requests. So this is where the Disruption Budget Manager fits in the picture that we've started to draw here. It creates the default PDBs, and it watches the Datadog monitors, our distributed lock system, to update the spec of the PDBs. And finally, it intercepts eviction requests at admission to validate them.
Nice. Thanks, Adrien. So yeah, we were starting to draw adding more components to that picture. But we've discussed provision of nodes, so the scaling, the Eviction API, but we haven't really started talking about how we start draining some of the nodes. I guess kubectl drain that you mentioned, David, doesn't scale very well to thousands of nodes. So how do we do it?
No, it won't scale. Even if you script it, that would probably not be a good idea. So as often in Kubernetes, when you want to do some automation, you would use controller. And this is exactly what we have done with something that we call the drain control. When we started the project back in 2020, we found an existing controller that is called Drain, that was delivered by Planet Lab, that was exactly fitting this purpose. I mean, It was looking at nodes, finding nodes that were tagged in a given way. I'll come back to that. And schedule a drain for that node. It would, at the time of the schedule, it would cordon and drain the node. So for a while, we have been running this controller internally to do the drains of our nodes. We have bring some contributions to this open source service, but also we have hit some limitations while we were also asking and providing new features. But more than anything else, during this period, we have grown our experience of what it means of doing disruption at scale on thousands of nodes. And this is why at the end of 2022, we realized that Drano was not the good fit for this exact scale. And we decided to write our own controller that we call the drain controller. So for example, Drano was scheduling drain, I said. That means that once he identified a node candidate for drain, it would put a schedule in 5 minutes from now. And he'd find a second node. So he would put another schedule for this node in 10 minutes and another one for the third node in 15 minutes and so on. So this works well when you have 3, 4, 5 nodes maybe. But when you have thousands, you end up having schedules of train for the entire day and sometimes weeks. And of course, the context of the cluster is changing during this period. So it's not working well. So this controller, this new controller is clearly dealing with the system in a different way. It's kind of continuously looking at the state of the system and deciding what should be the best options in terms of drain now. And this is really a big difference with the Drano controller that we used to run. And of course, by doing this rewriting, also we took the opportunity of adding more features that I'm going to explain. But how do we drain really inside this controller? 90% of the time, if not more, we are using the Eviction API that Adrien has just described. But there are still few cases where this does not work. The applications are not compliant with this way of doing the eviction. Because, for example, databases would have some specific logic to run before tearing down a node, like you can imagine, like rebalancing data to another node to ensure the level of replication, these kind of things. So to cope with this exceptional situation, we have defined what we call Eviction++. Eviction++ is nothing but the Eviction API that we used, but not against Kubernetes, but against a controller of the application, a controller that knows perfectly the application and what is the logic to be applied before doing a pod eviction. We clearly don't want to host this logic in our controller at infra level. It's a kind of a business domain, if you prefer. So we have a contract, it's the Eviction API, but the endpoint is not Kubernetes, it's the application itself. Also, we have introduced some new feature like pre-activity. Pre-activity is an opportunity for an application to do something before the drains actually happen. The contract is that the application declare the pre-activity as simple as putting an annotation saying pre-activity X on the pod. And the drain can only happen when this pre-activity is marked as done. And in fact, who is marking the pre-activity as done? It's the application itself. When it sees that the nodes become drain candidate, it would run its runbook for this pre-activity. And when it's done, mark the pre-activity as done. So this pre-activity acts as, it's kind of a gate to eviction somehow. We could not have used pre-stop hook on pods for that, for example, because you cannot block really. So this is why we created this pre-activity feature. If we look at the project, I would say that we had 3 phases. The very first one was really focusing on user experience, use cases, and adoption. And for example, during that period, we introduced a feature to deal with disk management. We had to evict the pod, but also we had to take care about the PV and PVC life. I mean, what do we do with the data and the disk associated and reclaimed by the pod? We have introduced something called pre-provision. When you do an eviction of a pod, you end up having a pod pending. And if there is no node, you may have to wait for a scale-up done by the cluster autoscaler, as explained by Adrien. And if you do not want to wait for that period that is usually lasting a couple of minutes, what you could do is, like, before running the eviction, asking the cluster autoscaler to provision the machine, and then only you do the eviction. And this time you have like a rescheduling of the pending pod within seconds. Eviction plus I explained. And one important thing was observability. Because we're creating disruption, application owner wanted to know why it's happening, at which pace this is happening, if it's okay to do it, and so on. So observability was really important to gain adoption. The second phase was really stability, ensuring that by creating disruption, we are not making any problems in terms of stability. So we introduce drain buffer, that is the time between two drains for a given application, stability period, how long the application should be stable before allowing a drain. So this is on top of PDB. PDB is good, but it's missing few things, in fact. Priority on pods. If you have an application that is having like a leader and follower, for example, maybe you want to drain all the follower first before moving the leader and draining it. So priority on pods. Pre-activity I've already explained. And finally, we have deal with velocity. Why velocity? Because when you want to do this at scale and you want to do what I would call mass eviction, meaning training the entire cluster, maybe, you need to do that in a reasonable time, maybe, because you are deploying a patch, a security patch, and you want this to be run as soon as possible. So to improve our velocity, we have created features that allow us to group workloads, to do parallel drains. Adrien also explained that we can do simulation that allow us to pick the right node at the right time to be sure that we are able to finish the work that we are starting. We introduce some priority between conditions that we have on nodes. For example, it's more important to drain a node that is not healthy because it has, for example, disk corruption, than a node that is going to be retired in 1 week or two. And of course, because we talk about velocity, we are doing more and more drain faster and faster. And it's important to capture back pressure signal from the rest of the signal of the system, like the cluster autoscaler, to be sure that we are not putting these components at risk. Because while doing a lot of eviction, the cluster autoscaler has to work a lot to create new nodes and tear down the old ones. So yeah, these were 3 phases that we went through. And all this is backed by this drain controller that is consuming the Eviction API. And this controller is reacting on tag node. In fact, inside of tagged, I should say, node with conditions, conditions being a part of the status of the node. Adrien, do you want to explain how do we get conditions on these nodes?
Yes. So yeah, like you said, the drain controller reacts to conditions on nodes. And so the part of the system that is responsible for putting the conditions on the nodes is called the node problem detector. There's an open source tool actually called node problem detector. It's maintained by a Kubernetes SIG. It runs as Damon said. It's actually available in GKE and AKS, and it runs several checks locally on the nodes. And if it finds basically health issues or health conditions, it sets them as conditions on the node. Conditions is a field in a Kubernetes node status. And also it publishes events. Now, since we're an observability company and we already have a demo set called the Datadog agent that watches health metrics on nodes, we don't need the same logic to be done again. So we can actually run a simple controller that we call the Datadog node problem detector, and it actually leverages the metrics that are already collected by the Datadog agent, pushed to the Datadog product, and then we have monitors that are configured to detect conditions, so the controller watches the monitors. This time, the monitor integration is not to protect the pods, like I said earlier, but to signal problems on the nodes. And by doing that, we're also able to consume metrics that don't come necessarily from the nodes themselves, but from cloud provider integrations, like like that's how we get the signals for host retirement, for example. And of course, we can also, there are also some conditions that are much simpler, like lifetime exceeded. We have a condition that's called lifetime exceeded, and for that we just look at the creation timestamp of a node, and if it's above a certain threshold, we put that condition on the node. Yeah, so here's where the node problem detector fits in the big picture. Watches monitors, different monitors, and sets conditions on nodes. There are many conditions in our system that our system handles. And so at first, we were focusing on healing problems on nodes, like hung tasks, failed disks. And that's actually now a minority use case of our system. And we leverage the same, same features, the same system for compliance and maintenance conditions. Like I said, lifetime exceeded. Depending on the environments, we don't want nodes to run for a certain number of days, more than a certain number of days. Or if node groups are updated, we're able to automatically drain the nodes to get the latest spec on new nodes. Or if Kubernetes is upgraded, that's also a condition, a cluster upgrade. And more recently, and that's picking up, we're also using the system to rotate nodes that are not using optimal configurations, or that use instance types that were sort of fallback instance types, but now the main instance type is available again, has capacity on the cloud provider side, so we can use it. And so we do more and more of the optimization kind of condition.
Good, thank you. It's nice to see how something that was created, a software that was created to do something else in the end is used for a lot more. That's great to see. So very quickly before we go into Q&A, again, if you have any questions, please use the Q&A button in Zoom or just put a comment on LinkedIn. David is going to put some examples on what we call mass eviction.
Yeah, I mentioned earlier mass eviction. But before being able to do mass eviction, what we had to do in the project, it has to have a good coverage of this automation. Today, we are at 98.6%, which is cool. And thanks to this, we are draining thousands of nodes every day. And if someone asked me, like, when are you doing mass eviction? Basically, my answer today would be always. We're doing that all the time now. Because if you think about it, Kubernetes upgrades, we have 3 times a year a release of Kubernetes. So if you want to keep up with the version, already this gives you like a pace. Plus you add on top of this a vulnerability that are published for the different layers, systemd, kubelet, operating system, containerd. You are always creating new node image that needs to be rolled out. And Adrien has just described that optimization is becoming a thing also, and we are doing that also more and more often. So yeah, quickly, there are some challenges associated with mass eviction. I'm going to focus on only one here, and I would pick cross-cluster management. When you run Kubernetes at scale, you need to run multiple clusters for resiliency purposes, and your applications are distributed across these applications. And here is a problem. PDB are inside the cluster. They are not cross-cluster resources. And so what we did is, thanks to the controller that Adrien has described, it's called the Disruption Budget Manager. We have been able to create a bridge between the PDB. So at admission time, we are verifying that the other clusters would tell us that it's okay to disrupt the workload here locally because everything is going well on the other side. So yeah, that was an interesting piece to deal with. And of course, when you do that at scale, you always have some application that fails or so on. Quick example, Dirty Pipe in 2022 was an opportunity to run mass eviction. We started by testing few nodes, 14 manually, tagging them. Everything is fine. The new image can be rolled out. We tag the entire fleet. We let the automation run night and days, working days and weekends. And within a month, our entire fleet was replaced. Other case, we are replacing the Kubernetes version, the kubelet version. So we move from a light blue to a dark blue, let's say, here on this slide. And the count of drain by the automation is represented in purple. If we add the number, you could see that the number of drain is a bit lower than the number of nodes themselves. The reason is some nodes just are just rotated naturally. They get empty, and so they are teared down automatically by the system without going through the drain and the automation. So yeah, that's it. This is what I call mass eviction.
Good. And so we have completed the life of a node with all the controllers the node lifecycle team has created. So we are going to go to questions. Before that, just call out, we have several talks by Datadog engineers at KubeCon North America happening next month. So if you happen to be there or you're attending virtually, Hemant and Laurent are going to be keynoting about an outage that Datadog had back in March. They're going to explain what happened and some of the things that we're working on to based on that outage. Some of them we discussed already today. And Adrien as well. Adrien himself is going to be giving a session at KubeCon. Adrien, do you want to introduce your session for people who may go there?
Yeah, so I'll be speaking with another colleague of mine, Ryan McNamara, about how to carefully replace thousands of nodes every day. So here the keyword is carefully. We'll be looking at focusing on the part about limitations of the Eviction API and how to make it bulletproof for replacing all those nodes.
Good. So yeah, some discussion about how to improve Kubernetes itself going forward. So thank you both. We are going to go for questions. If you think these problems are interesting and you want to join us, you can go to our careers page, datadoghq.com/careers, and we have openings there, not only for the compute team, but for many other teams in engineering. So I'm going to stop share now. And if you have any questions, use the Q&A button in Zoom or just put a comment on LinkedIn and someone will put it on Zoom so I can see it. The first question, actually, the three questions come from the same person. Come on, everyone. We need more questions. So Tobias says, how does your share nothing approach for service storage influence the design? How do you design the cluster node lifecycle in regards of design decisions about things like active passive, provisioning times, and potential high impact design choices like using Cilium cluster mesh in an active setup across AC zones per cloud provider?
Ooh, long one.
Yes.
I'm not sure it's completely related to node management, because it's more like, how do you place your workload between your set of clusters, which is not a topic that we have addressed today, but it's a very interesting one. For sure, I mentioned that we are doing a cross-cluster PDB bridge, and this is because we are deploying our application on different clusters, sometimes each cluster being in a different availability zones. And yeah, cluster application, what I would call application placement, is an entire topic here. This is not the purpose of the presentation. We are just serving node where there are pending parts. This is more the point here. I don't know, Adrien, if you want to add more on this.
No, that's good. Thanks.
Okay. The next question is, do you have a different approach for a cluster that hosts core workloads that are more directed to support Datadog internally, like CI/CD runners or the security-sensitive workloads?
It's kind of the same answer, I would say. It's application placement. The answer is yes. For things that we are running for internal purposes, we have dedicated set of clusters, depending on the nature of the activity, CI/CD, security. We have different clusters in different regions with different policies even. Yeah, it's also application placement. Here we are talking about specific application relative to the how we run Datadog. Anything else you want to add, maybe, Adrien? Or...
I mean, yeah, we try to reuse this approach as broadly as possible, but we do have some nodes by design rotate very often and don't necessarily require this type of a system.
Good. Okay, the next question is internal. You mentioned internal log system. Any chance that temporal is involved in this?
You want me to take it, or you take it that way?
Go ahead, David.
So no, it's not temporal behind the scene. I'm not the expert on it. I know that the first version was based on Zookeeper. I don't know exactly if it's still the same, because we were consuming an API. So when we developed the first connection between our automation and this locking mechanism, I heard about the internals, and I can tell you that it was Zookeeper at that time. I cannot promise that it's still this behind, but I don't think it's temporal.
Good. The next question is, are your nodes truly immutable ephemeral? So every update config change means a node replacement.
Yes.
Yes, they are.
Simple answer.
Simple answer, yes.
Yeah, I think if you attend the keynote, you will understand that it's completely the case now. It used not to be the case a year ago. And this automation that we have described is also part of a response of an incident that we had where some mutation were applied to the node, and it's not the case anymore.
Good. So we can say that now it's the case. Good. Okay, so we don't have any more. We don't have any more questions. If you have a questions, it's your last chance. You can ask anything about how we manage nodes in Kubernetes. And the person who asked the previous question had a similar issue that Datadog had. So I know they understand. So someone is asking a very broad question that could be anything. They want to cover something related about node management that it's directly related to security, which is very broad. But if you want to add anything, Adrien or David.
Yeah, so I mean, so part of our system can be used for security purposes, especially when we know about a vulnerability and we want to roll out a security patch. Then we use our system to drain the fleet and replace the nodes. Yeah, and we can also create some, like if we detect, we can use our monitor integration to create condition on nodes for specific security filters, for example.
Good. Any other questions? Going once, going twice. Okay, so we end up at the top of the hour. So thanks again. Thanks everyone for attending. Thanks David and Adrien for sharing your knowledge. This is, as I mentioned before, this is being recorded. So in a couple of days, it will be available in YouTube and also in our website, Datadog on datadoghq.com. So feel free to go there and share the link with your colleagues or watch again. Thank you very much and see you on the next one.
Thank you.
Thank you. Bye.